Imagine an industrial forge that melts down a fully formed steel beam, only to immediately recast it into the exact same shape. Every time you send a prompt to a transformer-based large language model, the system executes two distinct phases. First is the prephase phase, a highly intensive compute process that digests the input text. Second is the decode phase, which is heavily reliant on memory bandwidth to generate your output one token at a time. To bridge these two phases, the engine uses a key value, or KV, cache. This cache stores the complex attention tensors calculated during prefill, so the model doesn't have to reread the entire prompt from scratch before generating every single subsequent word. Standard inference engines like VLLM and SGLang tie the life of this KV cache to the immediate request. The millisecond the model finishes generating its response, the cache is deleted from GPU memory. In a 6-turn conversation, ephemeral state penalizes workflows. The cache dies after every response, forcing a fresh prefill over the entire accumulated history. Consequently, latency compounds. Time to first token degrades from 1 second on turn 1 to 18.5 seconds by turn 6. 17.5 seconds of that final delay is spent strictly recomputing the mathematical relationships of the exact same words from previous turns, simply because the user submitted a new query. In a typical multi-turn deployment, roughly 50% of high-end GPU compute is spent resolving math that the system had already finished minutes prior. This redundancy expands dramatically in document grounding or retrieval-augmented generation workflows. Consider an enterprise system where 1,000 concurrent users are asking different questions about the exact same 100-page PDF. Under the standard architecture, the engine executes 1,000 isolated prefill operations, burning GPU cycles to embed the identical source text 1,000 separate times. The industry operates on the assumption that transformer inference must function as a stateless API. LMCache challenges this requirement. It operates as an open-source layer that intercepts the KV tensors at the exact moment a request finishes, extracting them from the GPU and moving them into a persistent, shareable storage tier. Decoupling memory from the inference engine eliminates redundant prefill entirely, reducing required compute cycles and shifting the underlying economics of deployed LLMs. The architecture relies on an LMCache worker, a component installed directly alongside the inference engine, sitting exactly at the boundary of the GPU VRAM. This worker exposes 3 operations to manage state: lookup, store, and transfer. This chart illustrates how LMCache migrates state out of GPU memory. It routes from L0 GPUs down to L1 CPU RAM, L2 local disks, or L3 distributed caches. Instead of deleting tensors, the worker triggers the store operation, offloading completed KV blocks down the hierarchy. Routing state to an L3 distributed pool allows multiple independent Kubernetes pods or separate engine instances to query the exact same Valkey or Redis backend. If instance A processes a long document, instance B can pull that exact mathematical state from the storage tier the moment a second user submits a relevant query. Ephemeral request data becomes durable, globally addressable infrastructure. To make this system work, the engine needs a fast mechanism to determine if a new incoming prompt matches any previously stored memory. Here is the prefix hashing process. An incoming 2,000 token prompt is sliced into discrete blocks, typically 256 tokens long. The system generates a unique hash for each chunk, checking it against the global cache index. If completely malval, the index returns a miss. On a miss, the system executes a compute-heavy cold start. But if a second user asks a new question about a stored document, the function hashes the prefix, registers a hit, and injects those computed tensors directly into the GPU's VRAM. The engine completely skips the document. Only the novel suffix, the 50-token question appended at the end, requires new prefill compute. By bypassing the majority of the token sequence, LMCache benchmarks demonstrate a 15 times throughput gain in document analysis workloads. For repetitive context, the initial latency of a response is no longer bound by the length of the document. It is bound strictly by the length of the user's specific query. Decoupling the cache enables a major architectural shift: Prefill-Decode disaggregation. Prefill requires extreme floating point operations. Decoding is bottlenecked entirely by memory bandwidth. This comparison table outlines the standard hardware inefficiency. Without decoupled memory, Memory-bound decoding is locked to the same machine as prefill, occupying the expensive tensor cores of premium hardware like NVIDIA H100s. Portable KV states allow system architects to physically split the pipeline across discrete hardware profiles. The heavy initial prefill runs on specialized H100 compute pools. Once complete, the KV cache is transferred over the network via RDMA protocols. This data transfer between discrete compute nodes happens with near-instantaneous bandwidth. The cache arrives at a separate cluster of cheaper, high-memory L4 GPUs, executing the autoregressive decode phase. Treating attention state as a network-transferable asset isolates hardware requirements, allowing cluster-wide specialization without any application-level changes to the code. LMCache serves as a concrete implementation of Layer 3 inside the Agentic efficiency framework, decoupled memory. Moving the state out of the engine has a direct mathematical impact on the goal-to-energy output ratio, or GOR. This chart outlines token computation for a 10-round RAG session. Baseline execution requires 22,500 tokens, driven by 20,000 tokens of redundant document prefill. With LMCache, the document is computed once. The redundant segment drops to 2,000 tokens, shrinking total session cost to 4,500. The number of successful goals completed by the agent remains exactly the same. By shrinking the denominator of total generated tokens, reusing the KV state mathematically forces a 5 times improvement in the system's productive energy ratio. While the performance metrics are high, the architecture operates under severe constraints that challenge the lossless marketing claims surrounding prefix caching. The hash index is extremely fragile. A cache hit requires strict, byte-identical token sequences. A single altered word in a system prompt or a slight reordering of retrieved documents completely alters the hash and triggers a total cache miss. Looking at this visual scale highlights the second major constraint, the sheer physical size of key-value tensors. For a standard 7 billion parameter model, the resulting cache for a single 100-page PDF consumes over half a gigabyte of storage. At enterprise scale, the cost of distributed storage required for these heavy tensors can quickly eclipse the financial savings from reducing GPU compute. Lowering the latency and compute cost invites the Jevons paradox. By making individual calls cheaper, developers are heavily incentivized to deploy exponentially more agentic loops. Decoupled memory solves the multi-turn bottleneck, but systemic efficiency requires a rigid energy budgeting layer to prevent cheap compute spiraling into infinite unproductive loops.